So back to, there we go. So the takeaways again, many ways to approximate. Sorry, I'm just doing this for the benefit of the recording. Specific mathematical patterns. We're going to look at those in more detail today. Over and under estimation. We can make those conclusions under specific situations. We're going to look at more of those today. And we know that we are recovering information about how the function changes. That is the whole idea of accumulation. All right, sorry about that. Okay, so you have on that next piece of sheet of notes, you have four approximation techniques that you did in the notes, and we're going to generalize those for these conditions. So if you notice, just big picture before we start looking at each individual thing, we have the same four graphs in each section. Does that make sense, right? We've got concave up and increasing, concave down and increasing. Okay, right, concave up is this half cup, right? It looks like it will hold water. Concave down looks like it would spill water out. I call it a frown. I call this a smile and a frown sometimes. Concave up, decreasing means going down, concave down, decreasing. So all those four are for each one of the approximation techniques. And we're going to draw some general conclusions here. So we are going to do an LRAM 3 for this first row. What that means is we're doing a left rectangular approximation. So the rectangle that we're drawing between the function and the axis is the upper left-hand corner of that rectangle is going to touch the function each time. And we're going to draw 3 rectangles, which means each rectangle is going to take up 3 boxes. Okay, because I've got 9 boxes from beginning to end of this domain. So what does that look like? Well, and this is really kind of gaining fluency with drawing those rectangles too. So here's that first rectangle. Let me do that again because it's a little short and squatty. It's green. You see that point there in the left-hand part of the LRAM. And I'm just going to sweep to the right 3 boxes, just like that. There's my left approximation. And then at the end of that, I'm going to start my next box. So I'm going to go up to the function, find that point, sweep across 3 boxes. And then I'm going to start my new box. So go up and find that point, sweep across 3 boxes. There's an LRAM. Okay. Now we're not going to really do anything calculation-wise with it. We're looking at the pattern. It's a left rectangular approximation. These are all going to be LRAMs. So let's go ahead and sweep across with those boxes for the next graph. Left side of the box is touching the function. We sweep across. Left side of the new box touching the function, sweep across. Left side of the last box touching the function, sweep across. Doing okay? Okay, try to do the last 2. The last 2, the first box you draw is going to be, the first rectangle you draw is going to be really tall. Okay, colored pencils or markers might be handy. So left side of the rectangle, sweep across. It's really tall now. Now I'm going to come down here because my new rectangle is going to start right here. The left side is going to touch the function right where my little arrow is. Sweep across. And then my last box is going to touch the function right here. That's the left side of the last box. Doing okay? Any questions from home? Shout them out, please. Okay, that last one's going to look similar. The left side of my box, sweep across. The new box is going to start right here. It's going to sweep across. The new box is going to start right here. Sweep across. All right, so some general conclusions in terms of approximating and over and under estimates. Which one is an overestimate? Which one's an underestimate? I don't have too many people in the classroom, so if somebody at home wants to help out, they can too.
The first 2 are underestimates and the second 2 are overestimates.
Perfect, thank you. right? This is an underestimate, this is an overestimate. Okay? Underestimate just means that we've got not all the space between the function and the axis occupied by boxes, by rectangles, right? We've got, I call these gaps. We've got gaps here. So the rectangles aren't representing the full region. And here we've got too much of a rectangle. So it's an overestimate. I call those flaps, right? We should cut those off to get a more accurate area. Okay, so let's talk about what this means in terms of notation. Our typical notation is that we, since we need 4 locations to draw these boxes, we start out by labeling them x sub 0. So that x sub 0 is kind of like that first point is kind of like the 0 represents before I've drawn any rectangle. And then the x sub 1 is that I have drawn one rectangle. So the x sub 1 is after drawing one rectangle, I'm right here. And then after drawing another rectangle, I'm right here, and so on and so forth. So far, so good. So if we wanted to talk about expressing the sum of this approximation, the value, we can talk about generating a table of points, and you don't have to write down the table. But it looks like we're, generating a table of those x values and those function values, right? For this first point here, x sub 0, this function value is f of x sub 0. For this second x location, the function value is f of x sub 1. For this next location, the function value is f of x sub 2. And this last location is f of x sub 3. Now, if you notice, when we are doing an LRAM, we're not using the last point. Does that make sense? We don't use this. This last point doesn't represent the height of any of the rectangles. And that's true everywhere. In fact, I didn't even draw the last point here. I probably should have, but we don't use it. So I didn't even draw it. So this sum, then we could extend, we could extend it out any number of rectangles, which means this last function value would be f of x sub n. And so this left rectangular approximation looks like this. Delta x times its height, f of x sub 0, and the width is delta x, right? That's the width of the rectangle. And we could find the approximation by doing those 3 rectangles. This is in general terms, right? We would have numbers for this. In our notes, we had numbers for this. So far, so good. So what's important here in terms of your notes is to get the stuff in the red on the graph and get the summation. The table is just supplemental. All the information is on the graph. So this is the first rectangle, has a width of delta x and a height of f of x sub 0. Here's the next rectangle, the orange one, delta x and f of x sub 1, and delta x and f of x sub 2 is the last rectangle. And that's true for any LRAM. So what we don't use is that last point. If we wanted to extend it, if we wanted to keep drawing rectangles, the last rectangle would have the same width, and we would be using that point that's next to the last point. Remember how I said we don't use the last point? So if we don't use this last point, the one that's right next to it is n minus 1, or 1 before it. Okay? So their LRAM uses all of the functions up to the one just before the end. Doesn't use the end one. Any questions about that before we move on? Okay. So we're going to write it in what we call summation notation, which is this big sigma. It looks like an E with kind of like it's something has kind of poked into its back. Okay. And so we're starting at 0. In other words, we're starting right here at x sub 0. And we're going all the way out to n minus 1. And in general, if as long as we have the same width, we're going to take our function values times our delta x. And so that is the way to write it in what we call summation notation. Okay, so the big takeaway here is for LRAMs, we're using everything but the last point. Okay, that's the big takeaway. Everything but the last point. That's why we're starting at 0, because we're using the left side, and that's before we start drawing any rectangles. And then we're stopping just at the point before the last point. So any questions before I move on? Okay, so let's look at MRAMs. MRAMs are complicated because we need the middle. So look at this. We know that the first, we know we're taking 3 boxes for each rectangle. So we are going into the middle of that width, and we're drawing left and we're drawing right, just like in the notes. So now this next region, I'm going to go to the middle, put in a point, draw left, draw right. And then the last rectangle, I'm going to go into the middle. So I'm going to have to go way up here, draw left, draw right. Okay. So that now we're going to practice that 4 times. Find the middle, draw each direction. Find the middle of your width, draw each direction. Find the middle of your width that goes into, you're going to draw each direction. Middle of your width, each direction. Okay, last one, width of 3, my middle is right here. Draw each direction. Width of 3, my middle is right here. Draw each direction. Width of 3, my middle is right here. Need to come down here, each direction. So I'll give you a second to draw those, and then we're gonna ask the same questions. Over or under estimates? Is there anybody at home that needs some help drawing them? Let me know. Might be worth coming in tomorrow, because you do have the option of coming in. It is exam week. And then we start full face-to-face next week, so you can come in anytime. Unless, of course, you're quarantining, but that's a whole different story. I'm going to give you just a little bit more time to draw these. Okay, so what do you think? Which one's an over, which one's an under? Is it hard to tell? It's hard to tell. We don't usually ask you the questions, these type of questions for an MRAM for that reason. It's hard to tell. Now, I would say, you know, if you know a little bit about the concavity and all that stuff, you could probably make some guesses as to whether this little triangle thing with a curved hypotenuse is bigger or smaller than this, you know, and you can start making some educated guesses, but we don't ask you those type of questions because it's hard to tell. So we're difficult to estimate here, but more accurate than what we had before. So there's the advantage there. Does that make sense? We still use the same x0, x1, x2, x3, but because our dots are now in the middle of the rectangles, we have to average those x values to find the middle x value so we can find the function value. That makes sense? So what we're doing is we're saying, hey, my dot is between, come on, there's my dot is between x sub 0 and x sub 1. So if I know I have to be halfway between, if I take those, add them together and divide by 2, I'll get halfway in between. That's averaging. And then that I can stick into my function to find my y value. That's going to be the height of my rectangle. That's going to be the height of my rectangle, that function value. That's a little tough to wrap your head around. But the big takeaway here is MRAMs, when you will start to see in the notation, you will start to see fractions. That's the big takeaway, right? The LRAMs, you didn't see any fractions. The MRAMs, you'll start to see fractions. Okay? That also means we need the last point because we need to average it in. Okay? So your MRAM is going to be your same delta x's times this new funny function expression because we're averaging. And we can extend that all the way to the end. We can average the last 2 points. N is always the last point, so the one before it is n minus 1. Oh, sorry. We don't typically write a summation for this because it gets really messy. And I'm going to give you a little bit of time to write that down. Big takeaways, we start to see fractions in the expressions. That's the big takeaway. And we use all the points. Still missing notes from several of you, so just throw that in there as we're finishing up. Okay, so we can move on then to RRAMs, right rectangular approximations. And so RRAMs means we're going to go to the right side of that rectangle. So we know we're working with widths of 3 boxes. We're going to go to the right side of that, stick a point there, and draw backwards to the beginning. Then I'm going to go over to the right side of the next interval, draw backwards. In other words, draw to, I say draw backwards because I don't want to use the L word. I don't want to use left because that's a different sum. So I always say we go to the right side of the rectangle. We know the rectangle is going to be in these 3 boxes. We're going to go to the right side of the rectangle, stick our dot on the function, and draw backwards. Okay. Which means we don't really need that first point. I know I've drawn the first point, but we don't really need it. I'm not even drawing a rectangle until I get to the right side of my interval. So you go ahead. I'm going to give you a few seconds to draw those. Kristen Keeley, I assume you have your notes on. Yeah, I mean, just from the fact that you don't have a lot of questions, it's obvious you do. So we can start asking those questions again, over or under estimate. Yep, you got it. That's an over and that's an under for the reasons that we've discussed in the LRAMs. Is that the same as the LRAM response? Opposite, right? Because we're taking the other side of the rectangles now. So notice that, you know, it depends upon the type of approximation you do. It also depends upon not necessarily the concavity, but whether it's increasing or decreasing. Which is why we ask these questions only on functions that do one or the other over the interval, not both. If we have a function that increases and then decreases, that's harder to draw, you know, an LRAM and say whether or not over estimates because it changes. Boxes start out outside and then they go inside, you know, and that gets messy. So these type of questions are very specific, like I said. So we have functions that are strictly increasing or strictly decreasing. Okay, so I mentioned it. We don't use the first point, but we're going to use the same notations. So the same notation holds true. So if you have that notation drawn on the first one, it holds true for all the other ones. And so my ARAM is going to be this delta X, but it's going to be times F1. So we're using 1, 2, and 3 in this case, which means we're not using the first point because the first point's on the left side of the rectangle, and this is an RAM. And so if I wanted to extend this out more rectangles, we would have to use that last point in the table. So those are the patterns, is that if I'm doing an RAM, I'm skipping the first point and using the rest of them as heights. That makes sense? If I'm doing an LRAM, I'm using the first points and skipping the last point. Any questions about that? Looking in the chat, I don't see any questions coming through the chat. Nobody's speaking up at home. Hopefully you're all still awake. Just kidding, I know you are. Okay, so we can write the summation notation for this. The big difference is that we're going to start at 1 because that's what we have here. We're starting with, we're not taking the 0th point. You know, we're not taking the left side of that first rectangle. So we're starting at 1 and we're going to n. And otherwise it looks the same. So the big takeaway is to distinguish whether you have an L or an RAM is to look in this summation notation. Where am I starting? And where am I ending? And that is your indicator. And just to kind of preview, the topic questions today are literally just identifying notation. It's not like you're cranking out approximations or anything like that. That's I'm saving that for the con. So any questions about the RAM and the notations and the patterns you see? No, the summation, this, yeah, we can't write this from M. Well, we can. It's really messy, and they never ask you to identify it. If they ask you anything about an MRAM, they're going to give you this expression above, and all you have to do is say, oh, I have fractions. So it's either going to be an MRAM or a TRAP RAM, because we haven't talked about TRAP RAM yet. Those are the two where fractions show up. So that being said, here's our traparem. I like traparems. I call it connect the dots. I think it's the easiest to draw. You do need all the points. So there are all my points in my first approximation, and then you just connect them. You just go from dot to dot and then draw straight down. So dot to dot, draw straight down. Dot to dot, draw straight down. Dot to dot, draw straight down. So that's nice. But again, just like the MRAM, you need all the points. And then you just draw straight down. Get all the dots in place, draw straight down. Now this doesn't follow the rectangular over and under approximation patterns. Now all of a sudden increasing and decreasing matter, or not, excuse me, not increasing and decreasing, concavity matters. I'm just giving you a second to draw the trapezoids. Any questions about that? Okay, so what is the pattern here? If I'm concave up, what's happening? That means I got to look at these two. They do. How about in terms of over and under estimate? A little over, yeah, right. So that's an overestimate. And concave down, a little bit under. I would say, we definitely have a higher degree of accuracy here. It's tough to compare to the MRAM, but definitely the L and RMs. So now concavity becomes the determining factor for the traparem. We use the same notation. We don't like to mess with our notation. But now we're talking about, this is, I think, where I dedicated most of the time in the notes to setting traparem expression, right? Trapezoids have that funny equation, but it's really super handy for this application. Okay, it's half the height of the trapezoid. Careful, that's this dimension, because the height is measured between the parallel sides. So everything's rotated 90 degrees. So it's half of delta x times the sum of the parallel sides. So that's going to be my function values. So as we write this, that first trapezoid is half delta x times the sum of, and I did this in the notes, times x0 plus x1. And when we added them all up, what we noticed is that we only used the first height once and the last height once, but all the other heights in between we used twice. And that's the big time saver for traparems. So when we look at the green trapezoid, we use these two heights. When we look at the orange trapezoid, we use these two heights, which means we just doubled up here. When we look at the blue trapezoid, we use these two heights, which means we just doubled up here. So we doubled up for x1 and we doubled up for x2 heights, and then single ones for so that first function value and that last function value are only used once. Oops. Okay. And we can't write a summation for this one either. I mean, we can. It's messy because of this pattern here. We can write it. It's just messy, but we don't need to. We recognizing if you notice, this has a fraction in it too, but the fraction's out front, right? The MRAM, the fraction is in the function notation. So that's the big distinguishing factor there in that pattern. Okay. All right, so what are the different ways to approximate accumulation of change? Well, we've got 3 rectangular and 1 trapezoidal approximation method. Those are the standard ways. Okay, we have a unit 6 day 2 topic questions. Those should go really quick. You've got 20 minutes. It probably will take you 10 to get through those topic questions. They're just identifying the notation. And I see more people are coming in with their notes. That's awesome. I'm checking you off as you do that. So second semester, what I'm going to do is I'm in Infinite Campus where I put your assignment grades. I'm also in the comment section. I'm going to put whether or not you showed me your notes. Okay, so because that is a critical part to understanding the concepts and being able to discuss the nuances of the questions at a high level, a level of understanding you need. So don't kind of underestimate the value of that time taking notes. Okay, so go ahead and start the topic, day 2 topic questions. Not moving around enough. Not enough people in the classroom. The lights are turning off on us. I'm going to stop the recording, but obviously I'm going to be here till the end of the hour. Tomorrow is corrections. So for some of you, tomorrow might be corrections and catching up on this because I still am lacking some notes. So that's definitely doable. Don't despair. It's definitely obtainable goal. Right. I'll be here.